Hi, my name is Zepeda, and I have the privilege of quantifying the oxidation kinetics of a chromium-2 dimer complex this semester in integrated lab. So a little bit of background. Redox flow batteries work by converting chemical energy of the oxidation of one species and the reduction of another to electrical energy. So we're able to store energy in these redox flow batteries. But an issue that arises with redox flow batteries is there's a membrane that is separating these two species, and crossing over will occur, and then cross-contamination, and this will ruin the battery. So in order to combat this, what we do is we use the same element for both species. So in this case, we are going to be using chromium. We use it at different oxidation states for species 1 and species 2. And so when crossing over occurs, it doesn't ruin the battery. So chromium has a lot of available oxidation states to it. And one of them, chromium 2+, is a really good reductant. So it is able to reduce oxygen in the air and become chromium 3+. So it's a very unstable oxidation state because it is such a good reductant. And so in a way to better control that rate of oxidation, we attach ligands to it. And in this case, we were attaching an acetate ligand to our chromium dimer complex. So because it is so unstable, we were able to synthesize this, and we had to do it in a nitrogen-rich environment so that chromium did not reduce oxygen in the air. And then we were able to add oxidants and study the oxidation rate of this chromium dimer complex. So in scheme 1 here, we see our proposed mechanism of the dissociation and oxidation of chromium. So 1 is showing the dissociation of the chromium. So the chromium 2+ pops out of the dimer complex. And we propose that K1 is our slow step or our rate determining step for this reaction. And then 2, we see chromium 2+ reducing that oxidant and becoming chromium 3+. And we think that K2 is a fast rate constant in comparison to K1. So this is our fast step. So in order to study this, we used UV-vis spectroscopy, and we took spectra of our dimer complex every second for extended periods of time. So in figure 1 here, we see chromium 2 oxidizing in the presence of air. So like I said, chromium 2 can reduce oxygen in the air and become chromium 3+. So we see this at different times. So the blue line here is 1 second, the orange is 54 seconds, the gray is 143, and the yellow is 1,784. So I want to draw your attention to a couple wavelengths here. So 325 nanometers, we see this really large peak at 1 second. So that is our lambda max for chromium 2+. So that is where we can see chromium 2+ absorbing. And so as you can see at 1 second, we have the highest absorbance there at 325 nanometers. And that's because we have the most amount of chromium 2+ in solution. But as time elapses and oxygen is oxidizing the chromium 2+ to chromium 3+, we see that absorbance decrease. So for that yellow line, and the absorbance is way lower than we saw at 1 second of that blue line. But around 400 nanometers, 425-ish, we see the absorbance actually increase over time. So that is a very important wavelength of chromium 3+. So as more chromium 3+ is in solution, we see an increase in that absorbance at that wavelength, which makes sense because as time goes on and more oxygen enters, chromium 2+ is able to reduce it and become chromium 3+. So we're going to see more of that in solution and more of that being observed. So figure 2 here is showing us the absorbance versus time at those 2 different wavelengths. So the blue is 325 nanometers and that orange is 400 nanometers. So what we see at time 0 is that we have a really high absorbance at 325 nanometers, and as the chromium 2 becomes chromium 3, we see that absorbance dip down, and we see the reverse with that orange at 400 nanometers. We see that as absorbance is low, and as time goes on, we see an increase in the absorbance because there's more chromium 3 plus in solution. So we didn't want to just do this with oxygen, we wanted to look at oxidants. So we picked hydrogen peroxide. And so if you're looking at this graph, you may think that this looks different from what I showed you with the air, and you're right. So we see that at 1 second, this blue line here, we see that lambda max at 325, but instead of the absorbance decreasing there, as time goes on, we actually see it increase. So something really weird is happening here, and something very interesting, and that is what we believe to be another reaction is occurring between the hydrogen peroxide and something else in solution. So instead of, like we saw with air, 1 second having the most or the highest absorbance at 325 nanometers, we are seeing this overall increase in the absorbance. And so we have two reactions occurring here. So we wanted to create a model function for this. So what you see here is the blue is our observed data from the UV-vis. And the yellow here is our decay function. So this is the chromium 2 plus being oxidized in solution. And this other part, this exponential growth here, is the second unknown reaction that's occurring. So using Excel, we were able to get a best fit function for this. So that's our yellow line there. And then we were able to create a best fit function for that second unknown reaction, and that is shown in red. So we actually did this at different molar ratios. So we did it at a 1:1, a 1:5, and a 1:10. So for every 1 mole of chromium we added, we were adding 5 moles of hydrogen peroxide to solution. And we saw that there was an increase. It was dependent on the amount of hydrogen peroxide we were adding to solution. So that hydrogen peroxide is in our slow step or a rate determining step for whatever this unknown second reaction is. So we were able to do this using a global fit. So we added our exponential decay and our exponential growth, and we were able to create a global best fit for all of these reactions. So in blue here, we see the blue dots are that of the observed, and then the blue line is our global best fit for the 1:1 molar ratio. And then the yellow dots here are observed for the 1:5 molar ratio. And then the yellow line is that for our best fit. And then the purple dots again are the observed for a 1:10, and the purple line is our best fit, our global best fit that we were able to determine. So what we see here is actually, we see the K2, so that chromium 2 plus being oxidized to chromium 3 plus, we see that that has a very similar rate constant for the 1:1, the 1:5, and the 1:10. Meaning that this probably is not our rate determining step, so this supports our proposed mechanism. For the K unknown, we actually see that the rate constant does change depending on the amount of oxidant we were adding. So the hydrogen peroxide is probably in the rate determining or the slow step for whatever the second unknown reaction is. So our future work, we want to look at investigating what the second unknown reaction is to better determine what is happening when we add hydrogen peroxide to solution. We also want to study the oxidation kinetics for different, the oxidation kinetics of the chromium dimer for using different oxidants. So we want to see whether or not that K2 is the same no matter what oxidant we add to again help support our proposed mechanism. And then from there, we would add different ligands to find the ligand that helps us best control the oxidation kinetics. Thank you.